Hello, prop stats, and welcome to 4.3. We're going to talk about complements today, conditional probability, and Bayes' theorem. So you shouldn't need a whole lot. Simple calculator would be good, plus your data from our survey and your notes. So let's go. All right, we're going to calculate the odds of getting at least one. All right, and we're going to talk about what at least one means. And we're going to do the multiplication rule given other events. So the probability of at least one. When finding the probability of some event, okay, we should understand this. At least one has the same meaning as one or more. And then the complement of that, the complement of at least one, is there are no occurrences, or we have none. So we're going to use this no occurrences and complement to actually calculate the at least one because it's a little bit easier math. So now when we go through here, let's see if I can get my pen to work here. There it goes. All right, our notation. We're going to let A get at least one event. The probability of the complement would be getting none of the events. So this is red, probability of the complement. And we're going to find that. So the probability of A of what we want by 1 minus the probability of the complement. All right, let's go down here. Okay, Square Trade found that 6%, it does that at least once in every video. I don't understand. Okay, here we go. Found that it really is being grumpy today, isn't it? 6% of damaged iPads were damaged by backpacks. Okay, now 20 damaged iPads are randomly selected. So we didn't say they were by backpacks, they were just broke. Find the probability of getting at least one, all right, which the complement is none, that was damaged by a backpack is what we're looking for. All right, so let A be at least one iPad of the 20 was damaged by the backpack. So the complement of A is not getting any iPads damaged by a backpack. Okay, so we have to find the probability of the complement, and we're going to do that by taking the 1 minus the probability of the complement to find how many were actually damaged by a backpack. All right, so we know that the probability of damage by a backpack, or A, is 0.06. So now we want to find the probability of not damage by a backpack, or the probability of A's complement, is equal to 0.94. We took 1 minus the 0.06. All right, so now we have the probability of not damage by a backpack, but this is for one iPad, and we need it for 20 iPads. So to do this, we have to take 0.94 times itself 20 times, or 0.94 to the 20th power, and we get 0.29. So that's the probability of being not damaged by a backpack. So being damaged, at least one of them would be 1 minus this. So take 1 minus the probability of the complement. This decimal's in the wrong spot. 0.290, and we get 0.71. So the probability, all right, in 20 of our iPads, there's a 0.71 probability of getting an iPad damaged by a backpack. Well, if this is what I'm looking for, then my sample size is not high enough because this probability isn't large enough to guarantee I'm going to find one. So we would have to get a larger sample size to increase this probability, because the more 0.94s you multiply together, the lower this gets. And I'd like you to try that. What is 0.94 to, let's just double it, 40th power? What do you get? All right, I hope you got 0.084. So now the probability of at least one would be 1 minus the 0.084. And what do you get then? So now you have a 0.91 probability of getting one damaged by a backpack. Much better. So 40 is good. 50 would be even better, correct? All right, now let's play with one of yours. Okay, if you're looking at our third survey question, okay, we want to choose 5 people. All right, so out of 5 people, this is what we're looking at here. What is the probability of getting at least one left-handed person? Is this good to ensure we have left-handed persons? Okay, pause and try this. Okay, when I recorded this, you hadn't taken this survey yet, so I'm hoping you're following along okay. You should have done the probability of left, so taking the left-handed people out of the total number of people we had and divided those two, and you would have got a number. So this is my green answer here. The probability of not left is 1 minus this answer. So you're taking this number and you're taking 1 minus it. That's going to give you the probability of not left. So that's total in our survey. So now we have no left out of 5 is what we're looking for. So to do that, we take our probability of not left-handed. Should have said not, no. And taking it to the 5th power. So once you took it to the 5th power, you've got this answer. Now the probability of at least 1 is 1 minus that answer. And that is the probability that at least one of our 5 people would be left-handed. Okay, I hope you did a good job on that. Okay, conditional probability means there's usually, and it's almost always the words given that, but the probability of something happens after the occurrence of something else. So when you look here, it's denoted like this, and it's read the probability of B, and this is read right here, given that, that's how you say that, A has already occurred. So the probability of B, given that A has already occurred. This is the formula. It's the A and B over the probability of A. Now, let's show you how this works in an example. We have, if one of the 555 test subjects is randomly selected, so I have 555 people, that's what this says. This adds up to this many people. Find the probability that the subject had a positive test result, given that is very important because otherwise we do this differently, that the subject actually uses drugs. So this means that they have to actually use drugs, right? And out of those that use drugs, what is the probability that they will have a positive test result? So the blue is what is actually determining what's going on here. So we don't start here. We start with subjects that use drugs. That was supposed to be an S. So this is where we start. So we look at, okay, who uses drugs? So we go down to our thing, and the subject uses drugs are here. These are the people that use drugs. Those are the only people you get to choose from because it's a given that. Because the first condition is they have to use drugs. Now the second condition is they have to have a positive result. So out of these ones that use drugs, who has a positive result? And it's the 45. So when we look at this, we have 45 out of the 50 because the total here of all of my subjects that use drugs is 50. And out of those 50, 45 will have a positive test result. So we take the 45 divided by 50, and we have a 90, or a 0.9. There's a 90% chance that they will have a positive test result. Not bad, right? Okay, try your two. Pause and do them. Okay, so it came out like this. So this one here, your important part was does not use drugs, so you had to total that first. And there were 505 of them. And out of those 505, you should have gotten 25 that were positive, giving you a 0.05 result. Next one, we want to know the number that's positive. So now when you are at your chart, you are actually adding down because positive test result went, let's get rid of some of this. The positive test results were these. So you had to add this column here. All right. And then out of those, you had to choose. Usually when I start these problems, I add everybody up to start with so I don't have to go again. Like the first thing I would do is put in my totals because it's not too hard to do and it makes my math go a lot faster because I have all my values that I need then, regardless of what they ask. Okay, I hope you did a great job. Bayes' theorem or Bayes' rule. I've always called it Bayes' theorem, so who knows? Okay. It's a conditional probability to include application, which we use for revising probabilities when we have other information. So let's give you an example. This one's quite long. It goes from this page on to the next, so make sure you're paying attention. Got your highlighter out, and let's go. Okay, we're going to assume cancer has a 1% prevalence rate. Okay, that means 1% of the population has cancer. We know this. Because we know this, we can use other information. Okay, the event of cancer, we're going to say is probability of having cancer then is 0.01 for everybody in the US. Okay, now we're going to randomly select from the population. Okay, this cancer is included, we know PC equals 0.01. A false positive is 10%. What that means is we can get a positive test result, and then this is the given that right here. Given that cancer is not present. So 10% of the people who get tested will get a positive test result and they do not have cancer. All right, the true positive rate is 80%. That is positive test results, so make sure you know what you're looking at here. Positive test results. Now we've got our given that, right? And then we've got cancer is present. All right, I want to find, you look down here, the probability of cancer given that the test results are true. So if I get a positive test result, what are the chances that I truly have cancer? Even though we know some of these things is happening. So let's see what happens. All right, sorry about that. Okay. We don't have a number of test people, so we're going to make one up. And when you look at here, I'm just going to assume we have 1,000 subjects. And we use 1,000 because it's really easy to break that down into percentages and get large enough numbers to do so. All right, it's a good one to start with. We know there's a 1% prevalence rate. That means out of my 1,000 people, 10 of them will have cancer. All right, let's go down to our chart. So we have cancer and no cancer. Those are the two things we're comparing. Positive test result, negative test result. This is what we have. This is going to be our chart. So you're starting with these type column and row labels. That is all you know. All right, the next thing they give us is there's a 10% of the people will have cancer. All right, that's a total. All right, so cancer, I know I have a total of 10 people because 10 out of my 1,000, right? Well, if 10 of them have cancer, that means 990 of them don't have cancer. So this is where we start. So we go 10, 990. Those are the next things we can include. So that's what we put in there. I need different highlighters. I think it would work better. Give me a second. All right, so here you have 10 that we know, and then we subtract 1,000 minus 10, and we get 990. This we can do from that first sentence. That is all we have. Okay, now let's go back. To our next line. So we've done this part right here. 990 don't have cancer. So now we've got to figure this out. Among the 990 subjects without cancer, 10% get a positive test result. So 10% of my 990. So 10% times 990 is what you're doing. And that means 99 of these people are going to get a positive test result. So we go down here and we can now fill in this 99. Well, if 99 have a positive, then I can go and subtract the 99 from here, and 891 have a negative. We've got those numbers in. Now we got to go back up. Okay, so we've got these two filled out. Among the 10 subjects with cancer in the first row, 80% of the test results are positive. So 80% of my 10 have a positive test result. So we got 80% of the 10. So we multiply that together and we get 8. So we have 8 of these people are going to get a positive test result. And so 10 minus 8 means 2 will get a negative test result. So we filled in our two-way table. Okay, we've done it backwards, but we have done it. Now we can actually answer the question. So the question was, what's the probability of having cancer given that it's positive? So the given that is the positive. So the positive tests are here. So we've got to add these guys up. So this is the number that I want. Out of those, I want to know how many of them actually have cancer. Well, the ones that actually have cancer are, I think I just did that color backwards for you, didn't I? There we go. So we got to add this row up. Out of those that actually have cancer, we are looking at the 8. So we go from 107 down here, and the 8 actually have the cancer. So there's a 0.07% chance that they will actually have cancer with a positive test result, or a 7.4% chance. That's not too bad, because that means there's still a 92% chance that you do not have cancer. Make sense? Should help relieve some of those people's minds. So now I want to know cancer given that it's negative. So pause and do yours. So given that it's negative, you should have put 893 down here, because this is the row you're working with right here. And I want to know that they do have cancer, and out of those there's only 2. So what are the odds your test isn't going to be right if you do have cancer and need treatment? It's only 0.002, or a 2.2% chance that you will have cancer and not get detected and not get treated. Not too bad, right? All right, I hope you did well. Good luck on your homework. Make sure you post questions if you have any, and we'll see you next time.